Hey, y'all, let's finish up lecture 3.5. Should be problems 11 through 20. And I'm going to switch it up a little bit from what I did in the classroom. So if you were there for that, hopefully this will be a little bit different, at least some of it. All right. Applying a learning model equation. A common model for learning has an equation similar to K of t. Now, this is the new function. This is the transformation function. The original function is down here. So what they did is they took this function, f of t is equal to the t, which is what is represented currently. And they're wanting us to change it to have our transformations done where we have a -2 to the negative t plus 1. Okay, so this plus 1 means that we're going to shift. We're going to have a vertical shift, and it's going to shift up by 1. So let me show you something here. Let me go over each of these individually. If you have, we do have K of t is -2 to the negative t plus 1. The plus 1, let's see, is a vertical shift up 1. Okay, that's the plus 1. The -2 is a vertical reflection, and the negative for the t is a horizontal reflection. All right. So this is what we're going to do. Let's start by flipping it. So we'll do the negative t, we'll do our exponent first, just like order of operations. So we'll do the negative t first. So I'm just going to choose a couple points, and I am going to use my pencil for, because I don't want it to be staying the same. In fact, I'm probably going to erase it each time. All right, so we're starting here. I'm seeing some points. I see 2, 4. So I'm going to reflect it over across the y-axis. I see 1, 2. So I'm going to reflect it over. And that's going to go through there. I think I can make that work. All right, bear with me. Y'all know I cannot draw worth a darn. That's about as good as it's going to get. All right. So there is this is representing the 2 to the negative t. This is 2 to the negative t. That's our first part of our transformation. Now we're going to reflect it vertically. So we're going to have -2 to the negative t. I'm going to ignore the original one now, and I'm strictly focusing on the one I just created. And I'm going to reflect that over the x-axis. So it's crossing here. 1 and 2. So 1 and 2. Nope, 1, 2. There we go. And then 2, 4. So it's going to go like that. So now it reflected across. So this one is -2 to the negative t is what it's representing. This is y is equal to 2 to the negative t. Okay. The last one is we need to take the one we just created and vertical shift up by 1. So everything here is going to shift up by 1. There, and there. Okay. So this one I want to make solid. Helping 2. There we go. All right. This is the final transformation. And this one's representing K of t. Remember, name your baby. -2 to the negative t plus 1. All right. Let me know what questions you have regarding that. I am willing to meet with you on Zoom this weekend, or if we can get a group together to meet on campus or library. I don't care. Wherever we want to meet. I'll even use that piece. All right. Even and odd functions. That is our next victim. All right, determining even and odd functions. So even and odd functions, a function is called an even function if for every input of x, f of x is equal to f of negative x. So what this means, and I'm going to read this part, the graph of the even function, because this is important, is symmetric about the y-axis. It is symmetric about the y-axis. Okay. What we're going to do for this is we're going to substitute x for negative x. So substitute negative x for x. How's that? Negative x for x. And then simplify. If the outcome from that simplification is the original function, if original function, then it is even. Okay. If it is not the original function, it is not even, and you'll do the next step, which is check to see if it's odd. Okay. For odd function, for every input of x, f of x is equal to the negative of the f of negative x. So the graph of the odd function is symmetric about the origin. That is important as well. This is for odds and evens. So what we're going to do is we're going to, we've already substituted for x, negative x for x, and we've simplified. Okay. So at that point, we know it's not the original function, but what we can do is take that function that we got the outcome from and set it up to where we have, how can I write this? If we take that f of negative x and take the simplification and put a negative in front of that, if we then get the original function, it is odd. Okay, so we're going to plug in negative x for x. We've simplified, it's not even, so we're checking for odd. We're going to put a negative in front of that outcome and simplify again. And if it equals the original function, then it is odd. Or it could be neither. All right. So let's go with example 12. Is the function f of x equal to x cubed plus 2x even, odd, or neither? So I'm going to start with f of negative x that I'm substituting in everywhere there's an x. The thing I'm going to tell you to do, and this was a discussion in class, is how do we know where the negative goes? It's simple. The negative goes everywhere the x goes. So we're taking this x, and I created a parenthesis so that I can shove whatever I'm going to into it. I'm going to plug in negative x. There's another x. I'm plugging in negative x. We're now going to simplify. Nothing's happening on the left. That's just representing our function. Negative 1 cubed is just negative 1, and then x cubed. 2 times negative x is negative 2x. Okay, the original function is x cubed plus 2x. That is not what this is, so it is definitely not even. We've just proven that it's not even. Now we need to check to see if it's odd. To see if it's odd, we take what we have simplified, and I set up here, we're going to put a negative in front of it. Negative x cubed minus 2x. And we get x cubed plus 2x. That is the original function equals f of x. So it is odd. Okay. That is the steps to check for even. If it was even, it would have come out the exact same f of x here. It is not. So we had to take it to the next step further and put a negative in front of that simplified version. Distribute the negative. Remember, negative times a negative is a positive, and a negative times a negative is a positive. Please make sure you distribute to both. And because it turned out to be the original function, it is an odd function. Okay. All right. Vertical stretches and compressions.
I'm trying to think how I want to set this up. So what we're going to have here is if you've got a transformation of an original function f. So we are given an original function f, and we're transforming it only by multiplying it by a. And a is just a constant, it's just a number, but it creates a vertical stretch or a vertical compression depending upon its value. So if that value in front of this is greater than 1, then the graph is stretched. If it's between 0 and 1, not including either, then it's going to be compressed. Or if it's less than 1, if it's a negative, then there's a combination of vertical stretch or compression, and there's also a vertical reflection. Okay, so let's come down, and I'll talk more about A here in a minute when we get to a little bit further in. Graphing a vertical stretch, and we're starting with the function P, and it models the population of fruit flies. Scientists comparing this population to another population, Q, which is what this one is, whose growth follows the same pattern, but is twice as large. And it says, sketch a graph of this population. So we've got an original function P. What I like to do here, P of T and Q of T, is to represent just a few points off the graph. So we've got 0, 1, 3, 3, 6, 2, and 7, 0. All right. What you need to understand is the 1 through 7, which is your X values or your T values, is time. So these are your time. And the Y values is your what? It's the population. Okay. So what's changing here? They're saying whose growth follows the same pattern, but is twice as large. So it follows the same time pattern, but the population is twice as big. So nothing's going to change for my time values, my X values. The only thing that's going to change is the size, which is going to be my Y values or my function values. Okay. So 0 stays the same, but instead of 1, Q is twice as big. So 2 times 1, so the way to explain this probably is Q of T is equal twice the population P. Okay. So, and that's for any input T, Q is twice the value of P. Okay. So for 1, at 0, 1 is going to become 2. 3 is going to become 6. 2 is going to become 4, and 0 times 2 is still 0. All right, 0, 2, I'm going to plot. So 0, 1, 2, 3, 4, 5, 7, 2. All right, so 0, 1, up right here. And then, oh, we already had that one. I need to come down here. Sorry, I went to the wrong one, y'all. 0, 2. Ignore that one. 0, 2, 3, 6, 1, 2, 3, and 6. 6, 4, and 7, 0. All right. Same timeline. So it happens in the same amount of time, but twice as big. What? Oh, mine's shifted down. That's why. Okay. All right. Let me know what questions you have regarding that. All right, we're going to find a vertical compression of a tabular function. Vertical. Okay. So verticals, we've got 2, 4, 6, and 8. And then f of x is 1, 3, 7, and 11 corresponding to these x values. They're telling me there's a g function that is half of the f of x. So depending upon if we plug in a 2, f of x is 1, g of x is going to be half of that. All right, so if g of x is half of f of x, that's half of the y value, then I can plug in a 2 and find out what half of f of 2 is. Well, f of 2 is 1. So that is 1/2. All right. I'm going to go to G of 4. G of 4 right here is equal to half of F of 4. F of 4 is 3. Half of 3 is 3/2. Let's go with G of 6. And that is half of F of 6. F of 6 is 7. And so that is 7/2. Last one is G of 8. And that's half of F of 8, which is half of 11, which is 11/2. And that is for a vertical compression of a tabular function. All right, recognizing a vertical stretch. So this is a representation of the toolkit function for the cubic function. F of x is equal to x cubed. But this one's been transformed. It's got some vertical things happening with it. It's getting a little flatter here because the original one of these functions would look like this. The original cube would go through 1, 1 and -1. So it would be a little bit more like this. So you can see that this one is doing something a little bit different. So let's find out what it's doing. I'm going to have a G of x. This is going to be my transformed function. And since this is a vertical change, a vertical stretch, we're going to represent that with A. You'll see me always represent it with A. So understand that A is your vertical stretch or compression. All right. To find out which one it is, I just go through here and choose 2 points, or just choose 1 point. I need an XY value. So here's a pretty one right here. That is 2, 2 with my X and Y values. Okay. I know that my function G of X is Y. Okay. So Y is equal to A times X cubed. I've got values here I can represent for Y and X because they're on this graph. I cannot use 0, 0 because it's on the original toolkit function. You do not want to choose a value that this one shares with the toolkit function. It needs to be a separate value. 2, 2 or -2, -2, both would have been really good to use. So I'm going to plug in 2 for Y right here is equal to A times 2 for X, and it's going to be cubed. All right, so this is 2 is equal to A times 2 cubed is 8. Divide both sides by 8. A is equal to 2 eighths, but it can be reduced by 2. 2 divided by 2 is 1. 8 divided by 2 is 4. So A is 1/4. Therefore, I'm going to just take this where this A is, and my new function is going to be 1/4, and then it's X cubed. That is the answer. Okay. All right. Horizontal stretches. This is one I should do. All right. So given a function, the original F of X function, a transform function is F of BX. Notice the B is inside with the X, so it changes inside the function itself. B is a constant. It's either a horizontal stretch or a compression, depending upon the value. So at the value, if B is greater than 1, then the graph will be compressed by 1 divided by that B. If it's between 0 and 1, not including either, then the graph will be stretched by 1 divided by that B. If it is negative, then there will be a combination of horizontal stretches or compressions and a horizontal reflection. All right, so let's come down here and look at these. I am not going to look at this one at all. I want to just discuss if we're going off of this, what changes are gonna happen, okay? Ooh, I have a sticky note. Just to make us not see that. All right, so let's come up here. Suppose the scientist is comparing a population of fruit flies, those fruit flies again, to a population that progresses through its lifespan twice as fast. Through its lifespan twice as fast as the original population. In other words, the new population R will progress in 1 hour, the same amount as the original population does in 2 hours. And in 2 hours, it will progress as much as the original population does in 4 hours. Okay, sketch a graph of this population. So we're going to look at just the original population, and we're going to base things off of that. So I'm going to start with knowing what some points are. So I've got 0, 1, 3, 3, 6, 2, and 7, 0. Write those down. This is my P population. P is 0, 1, 3, 3, 6, 2, and 7, 0. All right, I'm going to have an R for the same. I'm going to create that. Now, what they're talking about here is the population value doesn't change. What's changing is the lifespan. So it's time that's changing. Remember, time is always your x-axis. So if the population is not changing, my y values are not changing, which means 1, 3, 2, and 0 are going to remain the same. What's going to change is my x values, which are my time values here. And they're telling us that what? R will progress in 1 hour the same amount as the original population does in 2 hours. And in 2 hours, as much as it does in 4. So it's cutting the original in half. It's cutting the original in half. So it's actually what? How would we say this? Well, if you plug in for 1, you're still going to have 0. Okay. So what we're going to say here is R of T is equal to P times 2T. Not times, P of 2T. Yeah, because that would cut it in half. So 3 divided by 2, 6 divided by 2, 7 divided by 2. And I'm just going to make those a little bit easier for us to graph. So the values are 0, 1. I'm going to make 3 halves, 1.5. 6 divided by 2 is 3. And 7 divided by 2 is 3.5. All right. So I'm going to plot these and see how this turns out. So 0, 1 is still the same original one. 1.53, 3, 2, and 3.5, 0. All right, so like this. Connect the dots here. All right. So this is saying that lifespan is cut in half, basically, for all of these. But there's still the original population. Cool. Cool, cool. All right, let's look at 17. Find a horizontal stretch for a tabular function. Well, horizontals, we're going to have to change the x's. So if function f is given as table 13, that's this here, create a table for the function g such that f of, oh, it's 1/2 of x's. Okay, so we need to know half of x is equal to 2. All right. Let me just see how I wanted to say this. Yeah. G of x is equal to f of 1/2 x. So our G input values need to be twice as large, need to be twice as large as F input values. All right, in order to have the same outcome. So where X is 2 for F, we need X to instead be, I like to look at it this way also, half of what is equal to 2? Well, half of 4 is equal to 2. So 4 is my first X. All right, I'm just going to follow through with just this one first. So if half of 4 is equal to 2 and X is 4 for G, then G of 4 is equal to F of 1/2 times 4, which is F of 2, which is equal to 1. And this is the whole setup. So G is 1, G of 4 is 1. The next one, we need to double the 4 basically. 4 times 2 is 8. 6 times 2 is 12. And 8 times 2 is 16. For each of those values, when you plug in G of 4, that will give you G of 8 will give us F of half of 8. Half of 8 is 4. F of 4 is 3. Okay. G of 12, F of half of 12 is F of 6. And F of 6 is 7. G of 16 is equal to F of half of 16, which is F of 8. F of 8 is equal to 11. So therefore, G of 16 is equal to 11. There was something else I wanted to say about this. With this one in particular, it was stretched horizontally by a factor of 2. Well, we already knew that. We already knew that because the horizontal factor is based on B. It's based on B. So, oh, we haven't got to that yet. We really not? Oh yeah, we talked about it earlier. So the B, this is B right here. So the factor is just 1 divided by B. And 1 divided by B is 1 divided by 1/2. Keep switch flip, and that's equal to 2. Okay. And I'm trying to think if there's anything else I need to tell you about that one. I think that's it. Yeah, we already knew it was a factor of 2 because of the B. All right, let's go to recognizing a horizontal compression on a graph. Relate the function G to F. So the original function is F, and we're going to relate the transformation function of G. So I'm going to start by looking at some points here. I've got 6, 4. This is my F, is 6, 4. And let's go with what? This is a nice one. 3, 3. All right. Well, our G functions, for the same ones, would be 2, 4 and 1, 3. Huh. Well, from 6 to 2, that was basically cut by a third. So 6 to 2 is a 3. And 3 to 1 is a 3. So G of X is F of 3X. Now this is our B. And B is greater than 1. So F is compressed by 1 over B, which is 1/3.
Okay. And that's how I figure those out. I want to kind of introduce something I haven't really talked too much about. I've used it for myself, and it's kind of something that I like to use, and hopefully it will help you as well. We're about to start talking about a bunch of different things, and let's just start with, I have a transformation function G, and it's based off an original function. And this is a whole new problem I've not talked to y'all about. Original function F would be f of x. So my transformation is going to be g of x. And g of x, if it has a number out in front, I'm going to talk about each one of these. X minus h plus k. If it has a number out in front, this is going to be a vertical stretch or compress. Vertical stretch or compression. Unless it's negative, then it's going to flip over. It's going to reflect compression. K is a vertical shift. Okay. H is a vertical shift. I'm sorry, horizontal shift. Ooh, horizontal shift. And that is H, not negative H, H. And then B is horizontal stretch or compression. But it's not the B. It's 1 over B. That's the tricky one. It's 1 over B. Okay. All right. Make sure you have that in your notes. I think it's going to help a lot with your transformation. Let's go to finding a triple transformation of a tabular function. So all of this right here is what I just went over in that one bit, to where I took g of x is equal to a, which is my, right here, my vertical compression or stretch. And then the function, if you have a b, then 1 over b is your horizontal compression or stretch, times x minus h. Oh, no, it's not x. Yeah, it is, it's x. H is your horizontal shift, and then plus k is a vertical shift. You won't always have every one of these, but just to understand what they each are will help you in writing your functions. So finding a triple transformation of a tabular function. Create a table of values for the function g of x is equal to 2 times f of 3x plus 1. All right, we're going to do each of these individually. We're going to start with the 3x. This is going to be a horizontal. Well, I can show you. Go back. What is 3? 3 is b. It's a horizontal stretch or compression. Okay, and it's 1 over b. So the way to look at that is, instead of starting off with 6, 12, 18, and 24, x has to start off with a third, 1 over b. So b is equal to 3. 1 over b is our stretch or compression. So it's 1/3. So we're going to take 1/3 of our x's. All right, because that's what we're doing here. So a third of 6 is 6 divided by 3, which is 2. 12 divided by 3, which is 4. 18 divided by 3 is 6. And 24 divided by 3 is 8. So that changed all of our x's. For each one of these, however, we're going to get the same values for f of x. So 10, 14, 15, and 17, because that just means that g of x, it needs to start with a different x value than f does to get the same outcome for y. Okay, let's go to the next part, which is 2 times f of 3x. So 2 times f of 3x means our x values are going to stay the same. And the only thing that's going to change is our y values. And that's just by multiplying times 2. So 2 times, because you notice it's f of 3x, which is this piece right here. So it's 2 times 10, which is all right here, 2 times 10.
which is 20. 2 times 14, 28. 2 times 15 is 30. And 2 times 17 is 34. Okay, the last piece of this is we've got f of 3x, we did that. We multiplied by 2, we did that. And now we're adding 1. So again, same exit values. And the only thing different is the g function. Let's finish it off by adding 1 to our y values here. So 21, 29, 31, and 35. Okay. Last one. Something else I wanted to talk about. All right, finding a triple transformation of a graph. All right, so this one is just taking the original function that they're giving us here. And we're going to do each of the things that it's telling us to right here. So if I've got, let's go with k. K of x is equal to f of 1/2 x plus 1. I need more space. K of x, f of 1/2 x plus 1 minus 3. Well, this right here tells me I'm going to have a vertical shift down. I do know that for sure. So let's look at each of these. This is my b, but I need to factor it out of this binomial. I need to pull it away from these two numbers. So half of what? Half times 1x is 1/2 x. And then half times what is 1? A half times 2. 2 times 1/2 is 1. All right. So this is my b. This is my h. Remember, it's x minus h. Maybe I should write it like that. So b, x minus h, and then minus 3. Okay. So the b means that we take 1 over b will be our horizontal stretch. It is our horizontal stretch. Okay. So what? 1 divided by 1/2 is 2. Okay. So we're going to have a horizontal stretch of 2. Cool. Horizontal stretch by 2. That's one thing we're going to do. Right here, we've got x plus 2, but it's supposed to be x minus h. H, because it's negative in front of it, this is not. So our h is -2. This is a horizontal shift. Horizontal shift. And it's going to be left by 2. Left 2. And the other thing we're going to do. And the last thing we're going to do is this -3. And this is a vertical shift. Vertical shift. And it's negative, so down 3. And that's what we're going to do to this little critter. I'm going to start by horizontally stretching it by 2, and I'm going to use a pencil for these. So from here, I'd come over here 2, and over here 2, and this one would stay the same. So this would be the next picture. Okay, so that one provides us our 1/2 because it's stretched by 2. Horizontal stretch by 2. The next one's a horizontal shift left 2. So from this function, we're going to shift the whole thing over 2. So here, and 1, 2, and 1, 2. So this one would be this little guy. Probably should give it a different flavor. This is my second shift. First shift. Okay. And then my last one I have to shift it down 3. So from the pink one, I'm gonna go down 3. 1, 2, 3. 1, 2, 3, and 1, 2, 3. There we go. And then that is K of X, which is, I'm not gonna write with this all. F of 1/2 X plus 1 minus 3. Always remember to name your baby. All right, so there's the final for that. Please let me know what questions you have. I went over things a little bit differently. Hope it helped. I also hope that it helped that I gave you that the A, the F of B, X minus H plus K. We're going to really use that a lot once we get into quadratics in the next module. All right, that's it. I will see you Tuesday. Good luck with practicing. Let me know if I can help.